Hello, and welcome to today's presentation for the 100 Gigabit Ethernet real-time recording system for the Xilinx RFSoC. My name is Bob Muro, and I'm an application specialist for Pentek, a designer and manufacturer of embedded systems. So today we're going to discuss traditional SDR, software-defined radio, versus the Xilinx RFSoC, real-time recorder applications and system architecture, data storage protocols and drive technologies, an example 100 Gigabit Ethernet streaming data recorder, and then a summary of all the material we've covered today. So to begin with, we have a traditional SDR versus a Xilinx RFSoC. So a traditional mezzanine card, or a COTS device, so that's commercial off-the-shelf software-defined radio product, are PCB mezzanine cards with data converters connected to an FPGA for processing. In the lower left, we see an example XMC mezzanine card. These mezzanine cards require a carrier to connect to a specific form factor chassis or PC motherboard for communication with an external network. In the lower right, we have an example PCIe version that would go into a typical 4U high server chassis. Now, the large chassis size often prohibits the RF inputs from being located close to the antenna. This is a key limitation as radio frequencies move into the higher microwave regions. This is the importance of the shift to the Xilinx RFSoC. This RF system on chip is a major new development for software-defined radio and contains A to Ds, D to As, ARM processors, in addition to the FPGA fabric. In the lower left, we have a block diagram of the Zinc UltraScale Plus RFSoC. The RFSoC can operate autonomously without the traditional chassis or motherboard restriction because of the onboard ARM processors. At Pentek, we make a version of this device on a small form factor PCB, and we refer to it as the SOM, or the system on module, pictured in the lower right. This SOM can also be installed in a small form factor weatherproof enclosure for close proximity to an external antenna, and that's pictured below. The small form factor enclosure contains two 100 Gigabit Ethernet optical ports that can transfer data to an external network. Now, the RFSoC data requirements, the 4 gigasample per second A to Ds can generate quite a large amount of data. So we're going to review some of the parts of the block diagram so you understand where it's coming from. So this green rectangle has the small form factor enclosure, or the 6350 is our model number, inside it. So you see the A to Ds, D to As, you see the entire device itself. We're going to focus on the SOM, which is in the purple rectangle, the 8 4 gigasample per second A to Ds, and then the two 100 Gigabit Ethernet optical ports to simplify the discussion. So the Xilinx RFSoC A to Ds can generate up to 64 gigabytes per second of streaming data. This is with a A to D that has 4 gigasample per second capability, each dividing 2 bytes per sample, and each sample 16-bit data sample for a total of 8 gigabytes per second per channel. And then 8 of those channels gives you the 64 gigabyte per second total of the data transfer requirement. Now, each 100 Gigabit Ethernet port has 4 bonded 25 gigabit per second serial lanes to transfer the data at the 12.5 gigabyte per second requirement. The 2 ports can accommodate 2 channels of data with some headroom. Now, real-time recorder applications and systems architecture. So what's an application that one might use a real-time recorder for? Well, it could be spectral surveillance and wireless channel sounding. So you might want to take some sweeping scans to evaluate the RF environment for a defense-related application or a 5G commercial one. If you look to the right, you see an API for our system flow software, and you see a frequency domain plot, a spectral shot, and a waterfall diagram when you want to review large long-term amounts of data. You could also be interested in electronic warfare, so you might have to record wideband radar signals during real time and then take this back to your facility for testing and review. Test and measurement equipment people sometimes make radar system simulators. So let's say you're testing a phased array antenna and you want to see how resistant it is to jamming per se. You might want to record some scenario so you can take it back to your laboratory for experimentation. And then also sometimes in the field of signal intelligence, you're required to go out in the field and then record an external environment so you can also bring that back and monitor that closely. All these applications require real-time recording. That means they can't be dropping samples. So the real-time recorder architecture. So real-time recording instruments are designed to record either RF analog or digital signals. An analog recorder consists of a software-defined radio front end installed in a PC with a RAID controller connected to multiple storage drives. The SDR A to Ds receive input from an external antenna array and transfer data to an FPGA for signal processing. The data is then transferred to DRAM memory for either buffering or moving directly to the motherboard depending upon speed, or an SBC memory, and it's usually via PCIe. And the lower left is a picture of a typical motherboard. The FPGA has multiple direct memory addressing engines to transfer this data and avoid unnecessary CPU intervention, greatly improving transfer speeds. The data is then transferred by the RAID controller and striped in parallel to multiple SSD drives at their maximum speed. And below is pictured a PCIe version of a RAID controller. The more drives in the system, the greater the total storage and the higher the aggregate sampling rate. More drives equal higher aggregate sampling. And pictured in the lower right is a typical 2.5-inch SSD type drive with a SATA 3 protocol. There's also a digital version of this recording device. A digital recorder is the same as the RF analog version, except the digitizing front end is replaced with a network interface card. And you see in the lower left a typical example network interface card with 4 QSFP transceivers. So a digital recorder can be used to capture the digitized analog data from any of our small form factor enclosures and Ethernet ports. So if you look below, you see 1 gigabit, 100 gigabit ports. It doesn't necessarily have to be that. We have other devices with 10 and 40 that can also be recorded. But for this particular presentation, the 100 gigabit Ethernet recorder is designed to capture the streaming UDP data from the Pentek version of the Xilinx RFSoC. So a little bit about the recorder system components. So below we see pictured the software-defined radio digitizing board, and that's the front end of the recording system. These boards are typically selected for their A to D channel count. In this example, it's 2. Sampling bandwidth, in this example, it's 200 megahertz, FPGA size, and then the data offload capacity. The digitized data is then transferred off the SDR to the motherboard for storage to disk ultimately. So the next part of the block diagram is a PC motherboard, or SBC, that accepts the digitized data in system memory from the SDR board. The data is sent over the PCIe using DMA engines from the FPGA, and then is transferred to the RAID controller for parallel striping to the storage drives. And then the final part of the block diagram is each individual rotating or SSD drive in the array accepts the striped data sequentially. So more drives in the array increase the maximum continuous streaming rate and total storage capacity. The maximum transfer rate is the total aggregate of all the drives in the array. So real-time recorder form factors, right? So one of the devices that you might want is a laboratory type device. These are the first implementation of our devices, and they are in a PC server chassis. And off to the right, you see a 4U 19-inch rack mount version that could either have rotating disks in an HDD or solid state drives. We also have devices that are portable, and these are a little bit more rugged. And so they have the same internal components as a laboratory version, except they have an attached keyboard and a screen, and they're often in this portable briefcase form factor here, and they will have 2.5-inch solid-state drives for improved rugged behavior. And then finally, we have a smaller 1/2 ATR version for very rugged, harsh environments, either in airplanes or on, rugged desert vehicles and things like that. And so they can take a lot of temperature variation and vibrations. So the data storage protocol and drive technologies. So just to review the storage devices. So you have an HDD, which is a hard disk drive with rotating magnetic medium. These offer the most ultimate amount of storage, but not very rugged. Then you have the SSD, so the solid state drive. So 2.5-inch standard form factor supports SATA protocols. This is an older version that supports SATA 3. There's some new type drives, the M2 being one of them. It's an SSD with a card form factor, and that supports the PCIe and SATA 3 protocols. There are more versions to this M2, but we're just using this one particular one to keep the presentation brief. There is also another U.2 SSD. Now that is a 2.5-inch standard HDD form factor. So it supports PCIe and SATA 3 as well. Now, each one of these drives has typical maximum read and write speeds. So the hard disk drive, the average read and write is about 80 to 160 megabytes. The older SATA 3 2.5-inch drives, about 550 megabytes per second. The newer drives that are based on NVMe or PCIe have read and write speeds that exceed 3,500 megabytes per second. We're going to focus on the U.2 SSD drive when comparing SATA 3 to NVMe protocols because this is the most popular one that we use in our recording devices. So SATA 3 versus NVMe transfer protocols. SATA 3 and NVMe are two methods or protocols to read and write data to a storage device. SATA, or serial ATA, is the older of the two technologies. The SATA cables have one transmit and one receive serial data lane. That's what limits the data transfer speed, or the maximum speeds, and you see that cable pictured to the right. The SATA protocol will continue to be used, but slowly replaced over time with the NVMe designs. Now, the NVMe, or Non-Volatile Memory Express, is a protocol designed for SSDs using a PCIe protocol that provides higher data transfer speeds by using multiple PCIe lanes like by 8 or by 16. And then the picture to the right is a U.2 NVMe connector cable, and that's using the PCIe lanes to transfer the data to the SSD storage drives. An example 100 gigabit streaming recorder. So the small form factor enclosure that we have has two 100 gigabit Ethernet ports to accommodate the 8 A to D channels. And you see that highlighted in blue in the block diagram below. So channels 1 through 4 stream on port 1, and channels 5 through 8 stream on port 2. Each channel has a unique UDP socket ID to simplify file sorting and data retrieval. Now the recorder itself must capture all of the samples from this small form factor enclosure. This design requires an FPGA for receiving streaming UDP data at that 12.5 gigabyte per second rate. Commercial network interface cards are not designed to stream data continuously at these high rates. Now we need a connection point, so we have an MPO, which is a multi-fiber push-on cable that connects both the small form factor enclosure and the 100 gigabit Ethernet recorder. Now, a QSFP28 optical transceiver, or 100 gigabit optical transceiver with a carrier, is the digital signal front end of the recorder. So we see the example optical transceiver on top, and then we look below at the block diagram and we see the blue rectangle where the QSFP28 is located. Now each UDP stream that's sent to disk via the dedicated DMA channel is illustrated in that block in the green rectangle. The host processor accepts the digitized data in system memory from the optical transceiver. The data is then sent over PCIe using DMA engines from the FPGA. And finally, the data is then transferred to the RAID controller for parallel striping to the storage drives, and that's in the purple rectangle. The specific model is the Pentek RTR 2757. So this 100 gigabit Ethernet recorder is designed to capture the streaming data from our enclosures, and actually all of our COTS products that output this 100 gigabit Ethernet. A single QSFP28 port for each MPO transceiver. There are real-time recording rates up to the 12.5 gigabyte per second, or 100 gigabits per second. There's front panel removable solid-state storage up to 122 terabytes. Each device has a dual Xeon Gold processor with up to 4 terabytes of DDR4 buffer RAM. And then it's all in an industrial-grade chassis. So in summary, we're going to leave this to the user to keep the presentation brief. And you can stop the recording and view these. And we also have some additional reading material, so high-speed real-time recording. The RTR 2757 Ethernet recorder overview, the COTS family of Xilinx UltraScale products, and then Pentek and myself would appreciate the fact that you have watched this presentation. Thank you.